Okay, I'm going to cover two more chapters this week, but we're not going to go in great detail, just information that you should need to know before you get done with this class. So we're going to go pretty quick, but properties of liquids is chapter 13. We talked about gases, and remember, gases, those particles are really independent. But when you look at liquids and solids, they're very rigid. There's not a lot of difference between a liquid and solid. They have very similar characteristics and whatever. And again, you look at the solid, you've got your particles that are really close, and a gas, they're really far apart. That's why gases are, their properties and their rules and all that are totally different than solids and liquids, because they are totally different. Okay, so in a solid, you have very close contact, but in a liquid, they're not that much farther apart than a solid, a little bit. Okay, so it's in between the gases and the solids. The particles are still pretty close, but they're fluid because they can slide across each other. That can happen in a solid. Okay, so there are a lot of attractive forces in between the molecules, not so much in the gases, and really strong in solids. Okay, so they have close contact, and they have attractive forces that allows them to move, slide across each other, so you can pour a liquid, but they're not like a gas where they're so far apart that they don't really affect each other. They do. They're very close together, so they have attractive forces that cause certain characteristics in liquids. Okay, when you're changing a liquid to a gas, it's called evaporation or vaporization. It depends on if you're adding a lot of energy to it. But when it changes from a liquid to a vapor to a gas, that's called vaporization. And you need energy for that to happen. You have to increase the kinetic energy for that to happen. Okay, so in order to do that, what you have to do is, by adding more energy to these particles, they move around faster, then they escape, then they become a gas. Okay, if you change from a solid to a vapor, not all substances do this. Okay, if you can go from a solid to a gas, okay, that is called sublimation. And again, there's not a lot to do that. Carbon dioxide, if you have the Halloween party where you have the foam, the steam coming out, carbon dioxide, solid carbon dioxide goes from a solid to a gas. It does not become a liquid. And iodine's like that too. Iodine crystals, they use them sometimes in forensics to get fingerprints off, but they go from a solid to a gas. They don't form a liquid as well. Again, that's not a common thing, but it's called sublimation. I don't know if I said that, but sublimation is when you go directly from a solid to a gas. Okay, things that can cause that is what they call vapor pressure. It's the surface of the pressure, or right at the surface of your liquid, the pressure that's pushing down on it. Okay, that's vapor pressure. And when molecules are in the liquid phase and they want to escape and become, a gas, again, that's evaporation. There's not enough pressure to keep them in the surface, so they escape. That's why if you leave something out, if you have 100 milliliters of water and you let it sit out, pretty soon you have like maybe 80 milliliters. Some of it you don't have to heat it up. Some of it will just escape because, again, the vapor pressure. So when you get molecules of gas striking the surface, they force some of them out. Okay, if you change from a gas to a liquid, and you guys will be experiencing this soon when you get frost on your windshield, what has happened is we have water vapor in the air. It hits your cool windshield, it cools off and becomes a liquid, and then it freezes and becomes a solid. And that's when you have to scrape your windows. But when it goes from a gas to a liquid, that's called condensation. Okay, in closed containers, there's an equilibrium that occurs between evaporation and condensation so that you stay at the same level. But if you have an open container, then you're going to get more evaporating than condensation. Okay, so again, when you go from a liquid to a gas, that's evaporation. When you go from a gas to a liquid, that's called condensation. Okay, and again, you can see here's what's happening in evaporation. You have more particles pressing down, forcing the liquid particles out. If you cover that, then you don't get that vapor pressure, and then they stay at the same rate. So you get becoming a gas and a liquid at the same rate, so it stays at the same level. In this one, where you have an open system, you'll have some of these particles escaping, and then you'll actually lose some of your liquid down here. Okay, so vapor pressure, again, is this pressure exerted on the surface. Okay, and it's an independent quantity. It increases when you increase temperature, obviously, because again, you're going to have the particles moving around faster. They're going to have increased temperature. So again, it depends on the attraction between the molecules in the liquid state. If the molecules themselves in the liquid are attracted to each other, then it's not going to happen very well. I mean, they're going to stay more in liquid than they are. But if they're a little bit farther apart, they're not quite attracted to each other, they'll escape. Okay, a volatile liquid has weak attractive forces. You can tell it's volatile very simply. Does it have an odor? If something has an odor, it's considered volatile. And what it means is it changes from a liquid to a gas easily. The most common, or one of the most common volatile liquids is gasoline. When you're pumping your gasoline, you can smell it. Some of it is changing from a liquid to a gas. And again, it gives off a smell, and that's how you can tell. Okay, here's using a barometer to measure liquids. You have, and we talked about this with gases with a force. You have it coming down, and it exerts pressure and then pushes it up the tube. This is our barometric pressure. We talked about it with gases as well. But a barometer can measure the vapor pressure of a liquid too. Okay, and again, the liquid, here in this case it's water, exerts a force on down here, and then it pushes it's not, this tube is closed. This is water vapor, but again, it pushes down here and forces the mercury up. And then you read it, and that tells you how many millimeters of mercury. That's why that's one of the units. If you're at sea level, it should be 760. And if you remember when we did gases, that was the standard. Okay. Liquids have, if you've ever noticed this, if you're sitting in your car and you see the droplets they kind of collect together until they get heavy enough, and then they fall down your windshield, but they form in droplets first. They don't just directly go down unless it's raining really hard. But the molecules, they're strongly attracted to each other. They have a surface tension, so they'll stay like this and form droplets. And then when they get heavy enough, then they cruise down. This is mercury. Mercury really has a high surface resistance. Okay, surface tension is kind of cool because we do have like a skin on water. If you go to the lake, there's a surface tension on the top of the water. That's why when you jump in the water and you do a belly flop, it hurts your belly. You have to break that surface tension to get, you're going to break it, because nobody's that light that they don't go in the water. But when you reduce your surface tension, when you dive, and if you've ever watched diving competitions, they make sure there's no splash. What they're doing is they're trying to reduce surface tension so that you go in the water smooth. The less splash, the higher your points, I think, when you're doing the diving. But anyway, surface tension is an attraction between the molecules on the top, on the surface, and they do form like a skin on the water. Okay, and again, when you jump in the water, you break that surface, and that's why sometimes if you're not quite in the proper position, it hurts a little. Bugs can cruise along because they use that surface tension, and so they can run across the water. The other thing with liquids is they're attracted to each other. So if you put them in a narrow tube, which is called a capillary tube, it will rise up because they're attracted to each other in the side of the tube. If you've ever had to give blood, they prick your finger and then they put that little tube on it and suck it up. They use it to test like your iron and stuff. That's a capillary tube. And the reason why the blood will go up that tube is it's attracted to each other. So capillary action is another thing that occurs. Or if you've ever done that where you've put colored water and maybe put a piece of celery in it, and the colored water goes up the tube of the celery, and pretty soon you have red celery instead of green or whatever. That's caused by capillary action as well. It's because they're cohesive forces in the molecules of the liquid. They're attracted to each other and they stick together. Okay? So we have cohesive forces and we have adhesive forces. Cohesive forces occur between the liquid molecules. Adhesive forces occur between the liquid molecule and the side of the glass or the side of the tubes. But both of them cause them to move up that tube. Okay, so that's capillary action. Okay, we also talk about meniscus. I'm sure you guys have heard of this. When you measure stuff, you're supposed to go by the curve, the lower part of the curve. What happens is the liquid's attracted to the side, so you get that curve. With mercury, it actually has more cohesive forces. It's more attracted to itself than it is the side. So instead of a meniscus going down like we're used to in water, it actually goes up. Okay, so if it's convex, the adhesive forces are greater. The adhesive forces between the water and the glass are greater than the cohesive forces in the water itself. If it's concave, where it goes up, then there's more adhesive forces here than there are in the mercury itself. So, but again, you get a different, most of the time, it's like this. And again, we read it down here. Here, we'd read it up here. Okay. And again, cohesive forces and adhesive forces are just in the capillary action of the whatever your substance is. Okay. Okay. When we talk about boiling point, we know that water boils at 100 degrees. That's if it's at sea level. If we boiled water, you guys, it wouldn't boil at 100. It'd boil a little bit less than that because we're not at sea level. But there's a vapor pressure on the top when it's boiling, and you have to overcome that to change it into a gas. Okay. So where is the boiling point of liquid higher? At above or below sea level? Well, it'd be higher at lower than sea level because then you have more pressure on it. Okay. So sea level, the atmospheric pressure is higher. Okay. So sea level is when it boils at 100. Okay. All right. Here we talk about different substances. Okay. Temperature when the vapor pressure is at 1 atmosphere would be at sea level. Okay. We know water boils at 100. Here we have ether and we have ethyl alcohol. And these guys boil at lower temperatures. Like ether, only about 35. And ethyl alcohol is about 80. So again, different substances, different forces. Vapor pressure is different, so they boil at different temperatures. Okay. Freezing and melting is another part of phase changes. Okay, the temperature at which a solid changes. So if melting and freezing occur at the same temperature, but solid is going from, solid to a liquid is melting, and liquid to solid is freezing. And again, just think of ice. Ice is solid. If it melts, it becomes liquid water. Liquid water, when it freezes, it becomes solid. Okay, this is part of a phase change as well. Okay, when both phases are present, when the temperature is at 0 Celsius, they're gonna freeze and melt at the same. They're gonna stay constant. If we go below, then they're gonna become more solid. If we go above, then they're gonna become more liquid. Okay, so again, we have forces in between molecules. Okay, we've talked about bonding. That happens in the molecule. All right, covalent bonding is in the molecule. But in between the molecules, we also have forces. Because remember, we have a lot of molecules. Avogadro's number in 1 mole. So that's a lot of molecules. So they're going to have forces in between them. And those forces allow us to form liquids and solids. Okay, that's the reason why they hang together, is because there's attractive forces in between the molecules. How much will determine your physical properties. The stronger they're held together, the higher the boiling point, the lower the melting point, because they don't want to separate. But if they don't have real strong forces, that's when they become volatile. Like most organic compounds are only have weak forces in between them, so they're very volatile. They stink, basically. They got a strong odor. Okay, so the stronger the attraction between the molecules in liquor, like I said, the higher the boiling point, because there's lower vapor pressure. They're going to hang together more. It's harder to break them apart. You have to add more energy in order for them to become a gas. Okay, these forces are, one of them is called a dipole to dipole, and here you can see in water, this is the oxygen, which is negative. Here's the hydrogen, which is positive. So they're going to have a force between. Again, this is not in the molecule, it's in between. And that's called a dipole, and it's a pretty strong force. And it's because of the positive and negative differences there. Okay, that's why water's polar. Okay, it's got a positive end and a negative end. Well, in between the molecules, you're going to have that attractive forces. Okay, they will align, and then so now there's going to be oxygen over here. There's going to be hydrogen over here. They're going to align so that the opposite ends, and that's what gives water its ability, again, to dissolve so many things because of this attraction with the positive and the negative. But a dipole is attraction between the positive and one pole and the negative pole of another. And again, it's in between the molecules. It's not in the molecule. Okay? Because of that, because water is polar like that, it has a high melting and a boiling point. Dipoles are strong forces. Okay? So because they have a strong force, they hang together. If they don't have a strong force, then they boil and freeze at different, like here, hydrogen sulfide, it melts at negative 85. Look at how cold it has to be. So it has a stronger dipole forces in it. So when you have that attraction between the molecules, it's going to change the melting point and it's going to change the freezing point. We didn't really talk about heat of fusion and vaporization. That's just the how much energy it takes for it to melt and to boil. And I'm done. I'm at 15 minutes.